Glider 2-1 Components and Systems. Welcome to the captivating realm of gliders, where the elegance of flight is achieved through a seamless blend of design and technology. Although gliders exhibit diverse shapes and sizes, most adhere to fundamental design principles rooted in aerodynamics. As air flows over glider wings, it produces lift, enabling the aircraft to stay airborne. Glider wings are crafted to maximize lift while minimizing drag. Early gliders featured wooden frames with metal fastenings, stays, and control cables. Later designs introduced fabric-covered steel tubing glued to wood and fabric wings, combining lightness and strength. Modern gliders utilize advanced materials like carbon fiber, fiberglass, glass-reinforced plastic, GRP, and Kevlar. Computer-aided software designs enhance performance, and high-performance gliders are primarily built with composites. Composites, including gel coat finishes, provide strength and lightness but are susceptible to UV radiation and moisture. Rigging and derigging become routine for composite gliders. Glide ratio, a measure of performance, increases with each technological advancement. Modern gliders boast low-drag laminar flow airfoils, and winglets reduce drag while enhancing handling. Bug wipers, akin to miniature windshield wipers, clear wings of insects. Water ballast, strategically used and jettisonable, acts as weight for strong lifts and adjusts the glider's center of gravity. Gliders actively compete in gliding competitions overseen by the Fédération Aéronautique Internationale, FAI. Various glider classes exist, each with its distinctive features. The standard class emphasizes simplicity, lacking flaps and maintaining a 15-meter wingspan. The 15-meter class introduces flaps, maintains a 15-meter wingspan, and allows water ballast. The 18-meter class incorporates flaps, features an 18-meter wingspan, and allows water ballast. The open class offers a limitless wingspan and a weight cap of 850 kg. Additional classes include the two-seat class, allowing a 20-meter wingspan for shared journeys, and the club class, accommodating various gliders with performance adjustments for fair competition. The World class introduces the Warsaw Polytechnic PW5, a low-cost glider fostering accessibility and unifying competitions under one glider type. As we explore glider anatomy, the airframes, fuselage, wings, and empennage play crucial roles. Self-launching gliders, equipped with engines for solo takeoffs and returns, add autonomy to the gliding experience. Now, let's delve into the intricacies of glider components, starting with the fuselage. Picture the fuselage as the beating heart of the glider, the anchor to which wings and the empennage elegantly attach. Within this pivotal structure, you'll find the cockpit, a cockpit that houses the controls dictating the dance of the glider in the skies, and a seat for each intrepid aviator. The materials used in crafting this central element range from traditional wood to modern marvels like fiberglass, Kevlar, and various composite wonders. Transitioning to the wings, these majestic structures come in sizes spanning from a modest 12.2 meters to an impressive 30 meters. Each wing is a canvas of aerodynamic mastery, hosting vital components crucial for controlling the glider's attitude and navigating the delicate balance of lift and drag. Ailerons, our conductors of roll, are perched on the outboard trailing edge of each wing. Picture this. When we command the right aileron to ascend and the left to descend, a harmonious roll to the right ensues, a ballet in the sky. Now, let's talk about lift and drag, the yin and yang of glider dynamics. Enter spoilers, dive brakes, and flaps, our choreographers of adaptability. Spoilers, those disruptors of airflow from the upper wing surface, gracefully induce a quicker descent. Dive brakes, extending their wings from both upper and lower surfaces, step forward to augment drag. But the flaps, positioned with finesse inboard of the ailerons, steal the spotlight. They dance between adjusting lift, drag, and descent rate. In cruising conditions, they may elegantly position themselves negatively, enhancing high-speed efficiency. A downward extension increases wing camber, lifting capacity, and the very essence of aerodynamic allure. In our exploration of simple flaps, we find three positions: trail, down, or negative. This is where the wings express themselves in symphony. Picture a downward deflection, a nuanced movement that increases effective camber, altering the wing's chord line, lifting capacity enhanced, drag beckoning. Negative flap settings, a secret of high-speed aficionados, gracefully reduce wing lift, curbing the very essence of drag. Yet, when we extend them upward, a subtle reduction in wing lift ensues, alleviating the balancing force required from the horizontal stabilizer, a masterstroke in glider dynamics. And so, understanding these components becomes our compass in navigating the intricate dance of glider control and performance. Now, let's set our sights on the empennage, the tail section that orchestrates stability and control in the glider's aerial performance. Within this dynamic ensemble, we find fixed surfaces, akin to the feathers on an arrow, and movable surfaces that respond to the glider's every whim. First, let's meet the elevator, a virtuoso attached to the horizontal stabilizer. It's the maestro of pitch, guiding the glider's nose up and down, dictating the pitch attitude. Picture the horizon as its guiding sheet music, ensuring a harmonious flight. And for fine-tuning, we have the trim tab, a subtle ballet on the elevator that lessens resistance on the controls, a nod to aerodynamic finesse. Next in our ensemble is the rudder, a luminary attached to the vertical stabilizer. It takes center stage in the dance of yaw, swaying the glider gracefully about the vertical axis. The rudder partners with the ailerons and elevator, choreographing seamless turns through the vast skies. Now, for a unique soloist in our repertoire, the stabilator. Unlike its counterparts, it pivots up and down on a central hinge point, offering a distinctive touch to pitch control. When the control stick pulls back, the nose elegantly ascends, a gentle push, and the nose gracefully descends. To complement this performance, an anti-servo trim tab steps in, mirroring the control feel of an elevator, a testament to precision in flight. And what about trim devices, those unsung heroes of glider control? Elevator trim tabs, bungee spring systems, and ratchet trim systems. These maestros alleviate pilot workload, ensuring a symphony of control. The trim tab, whether servo or anti-servo, collaborates with the primary flight controls, lightening the load on the pilot, providing positive feedback, and sculpting an aerodynamic masterpiece. Now, a glimpse into the evolution of the empennage's aesthetics. In the early days, the conventional tail dominated the scene, with the horizontal stabilizer gracefully mounted at the bottom of the vertical stabilizer. Some gliders embraced the T-tail, a distinctive formation with the horizontal stabilizer atop the vertical stabilizer, forming a T, and then, there's the avant-garde V-tail, where two surfaces unite in a V, merging elevator and rudder into a seamless performance, aerial poetry defined by ruddervatters. Such is the grand tapestry of the glider's tail, an evolution that mirrors the ever-changing dance of aerodynamic design. If you click like and subscribe and leave a comment, we will provide a coupon for a free PDF download, one of 9 ebooks. However, each individual can only download up to 1 out of 9 ebooks for free.